This conference will now be recorded.
Okay, good morning, everybody. Welcome to the OCP HPC sub-project regular meeting. On today is the 27th of June, 2023. So what I've got for today is, I believe we have a new attendee, so we'll have a quick introduction in a moment. Then I've started to put together a little bit of an action plan for actually creating an HPCM power and thermal test vehicle. But that will also help us go in the direction of creating a real HPCM module. So I'll get into the detail of that. Then I've been working with Ender from DS Tech and Chate from Rise with regards to some thermal simulations. So Ender's been starting that effort, and he has some things to talk through in terms of what he needs for the thermal model to get that going. So we'll just cover that part of it, and then hopefully we can move the ball forward on his simulations. And then with regards to the conference submissions, I have given an update. I have submitted something to the OCP, the main program, just to give people an update on what we're up to. And also, I would like to talk about a few other topics on a few other conferences that are coming up, and whether we should put something together for those. I think somebody just joined.
Hi, Alex Loveltroy.
Alex.
Los Alamos.
Welcome, Alex. Thanks for joining. So I'll add you to the list here. So actually, Alex, your timing is pretty good because we're literally just going into introduction of new attendees. So let me just start off with Pradeep Reddy. Pradeep, would you like to introduce yourself? Just a quick introduction and of yourself, what you do, who you work with, and why you're joining us.
Yeah, sure. Thanks, Alan. Hi, everyone. My name is Pradeep. I have around 20 plus years of technology experience, and I have started into application development side, Java and open source. Later, I worked with multi-cloud platforms and also on-premises infrastructure during my career. I'm also worked as a startup entrepreneur two times, and I have my own company. And also, I'm an angel investor in couple of startups and advisor mentor to them. And recently, I was working with Quiet Platforms, part of American Eagle, as a director, cloud infra engineering. I am based out of Bangalore, India. Thank you.
Thank you. Thanks. And Alex, would you give us a quick introduction, please?
Sure. My name is Alex Loveltroy. I'm with Los Alamos National Laboratory. My background in HPC is through Cray and HPE, always on the software side. So HPC system management, those kinds of things. My interest is in figuring out how the future of system management, what does the future of system management look like, given the changing form factors and the things like that. So I'm particularly interested in that area. My current contributions are all part of an open source project that isn't fully open source yet, for cloud-like supercomputer management. So that's me.
Excellent, Alex. I didn't realize that detail about you. That's very good. That's a big aspect that we need to work on. I've had some past experience. In fact, IBM have done a lot of donation into the industry on that area, And I think that's a big area where we could make a big difference here as well in a sort of a collaborative way. So your help on that front would be superb. I think that is the key, one of the key software areas. We're focused very heavily on the hardware, but the software side of the system management is going to be a rapidly changing area in my mind. Is especially, I'm not sure if you're familiar with OCP's CMS, the composable memory system work group, but CXL fabric management is one of their big topics, and you can see that there's a lot of work to be done there of how do you enumerate the machine and discover all the different pieces of memory that are all over the place and bring that all together. So that's a big management challenge
Yeah, totally. As we move to a more decentralized supercomputer,
Yeah,
how do I know that the memory I'm talking to is the memory I want to be talking to problem,
right.
and not some sort of rogue piece of hardware is a big deal.
Okay, no, absolutely. Oh, that's great. So I just need to pop you quickly into. I'm sorry, I spelled your name wrong there. Let me just pop you into my directory. Okay, and did we just get one other person just jump in here? Okay. All right. So thank you for the introductions. I don't believe we've got anyone else new, do we? I think that's all the existing ones. Okay, so, oh, sorry, I didn't change the titles here. My apologies. So my first one is so let's discuss the action plan for creating an HPCM power and thermal test vehicle. So let's start off with that. So just as a recap, I visited Oak Ridge National Labs a few weeks ago. I presented to them a sort of a view of Frontier as a machine if it was built out of HPCM modules, and presented a bit more detail on the wall of compute that we've been working on in a conceptual way, again, very conceptual. And we've now got a basic framework of how we believe we can power and direct water cool this architecture. And really, and we've also got our first candidate in terms of the Xilinx Versal FPGA, or they call it ACAP now, not FPGA anymore. One of their big devices. So the VP1802 or the 2802 that has a lot of AI engines on it as well. So I'm just really trying to tie that together and begin to build a project plan for us all to start to execute on. But what's clear to me is until we really have the thermal and the power infrastructure nailed down, it could be a bit dangerous to get too ahead of ourselves in terms of the module design as a whole. So we need to prove that. So Ender's and Chatte's simulation effort on the thermal side is going to be very helpful. But I also I thought it was going to be wise for us to build a test vehicle. I think some of these ideas may be a little bit challenging to accurately thermally simulate. I may be wrong, but that's really my initial thinking here is that we want to build a test vehicle, and I think we can possibly do this fairly cost effectively in a piecemeal fashion, and that will help to compare with the thermal models that Ender is working on. I see that Greg. Good morning, Greg. Thanks for joining.
Morning. Hi, everyone.
Just copy this in there. Okay, so I've pulled together some slides. Let me just go to the beginning of these slides. So hopefully you can see this. Can you? Yeah. So I've just titled this "Plan for OCP HPCM Power and Thermal Test Vehicle." So what I wanted to start with here is we actually came up with the architecture of this Versal Premium module probably well over a year ago now. And the nice thing about this particular FPGA or ACAP device is it does have a decent number of transceivers, 168 transceivers, so that we can fully connect, or not fully connect. We can actually get a decent amount of connections into this first HPCM module. We have been talking, for those of you that are aware, we have been talking to XConTech about potentially doing a CXL switch version as well. Obviously, the FPGA is a Swiss Army knife, and people are using it for a lot of CXL enablement, because that's one of the key areas that we see as if we can get maybe some attention. And we've also been talking to Fabrica with the potential of they've got an interesting switch chip that has both CXL IO on it. They see a shared memory model where you have the memory in the middle that can be shared locally with accelerators and processors, and also shared over an Ethernet fabric with a bit of a, I guess, a bit of a slingshot-like protocol over the Ethernet fabric. They've got their own proprietary low latency over Ethernet approach for shared memory. I'm hoping still to get them to present what they're doing, which would be helpful. So there are a couple of other modules specifically on the switch side that we can do.
Is there any flight plan there, Alan, within Fabrica?
Any what? Sorry.
Flight plan. When are they expecting to have parts and that kind of thing?
Yeah. So they showed their stuff off at MemCon. They showed a demo platform which I believe was running on FPGAs, and I believe, I don't know the details, but I believe they're looking at taping out later this year their first silicon. So yeah, they're on a little bit of a longer timeline, whereas XConTech, for example, have silicon today with their CXL switch. Yeah. Did somebody else just join? Callum, hi Callum, thanks for joining. Let me just add Callum in. Okay, yeah. But we've decided. I think this is prudent for us to move forward with an FPGA based one first. I think that there's a lot of things that we can do with this, and it's being heavily used, like I say, for a lot of the CXL developments, because you can do it in the soft IP. So again, this is just showing the block diagram is in the logical level. I also wanted to add in the fact that I will just get these animations. We can plug in all these different modules into these slots. Sorry, this is an old slide, so I should have turned off the animation. But we can plug cables or modules into here, obviously. The other piece of this, into Alex's introduction, is quite specific. Is we've in the OCP we have this DCSCM, which is a sort of a global security module that manages everything from a root of trust perspective. But we want standalone boot capability of all of these devices, or as I see it anyway, as we do move towards this distributed computing world. We don't know how these things are going to be configured at power on, so these things need to be able to self-boot and then be discoverable, and so we need some level of BMC in the actual infrastructure. As well as that, all of these modules we're supporting in this standard do have some level of sidebands. There's there's a big bun fight at the moment about should CXL have sidebands, have physical sidebands, have out of band over the transceivers, or in band, or all three. And so, you know, that's a moving feast. But we know that NVMe modules, in CXL.mem modules, and all of this, at the moment, they do have traditional sidebands. So we need to absolutely support this. One of the nice things is Lattice has been doing a lot of work in the I2C and I3C front in terms of aggregating a lot of these sideband signals over a single wire aggregator, and they also have something called a LVDS tunneling protocol interface, LTPI, that they've freely donated to OCP, and that's part of the efforts in OCP. And the nice thing about that is it helps routability in the boards, in us, because there's lots of pins. You know, there's a good number of pins on each of these connectors. So you can see these ICE40s in this picture. They're effectively collecting a bunch of sidebands from two of the IOs and aggregating them down to a single wire to pass them back to the BMC controller. Just hearing people popping in and out here. I just want to keep track of. Hi, Suresh. Thanks for joining.
Hello.
Oops, sorry. PQR. Multitasking here. Okay, there was no one else, was there? No. Okay, yes. So we've got that. These are tiny devices as well, so they can be mapped. We've already got them mapped on the boards, but in the middle we need this BMC controller. Now, again, one of the big efforts about making BMCs, they're a big area of potential hacking, and whilst we've got OpenBMC that has really gained tons of traction, we on the controller side, they've been dominated by a couple of smaller companies where their IP, their hardware IP, is very proprietary. So there's been an effort called LibreBMC, which IBM were heavily involved in, and a number of other companies, but OCP as well. And I believe LibreBMC is actually implemented on the DCSCM, the security module that OCP have created. And there are two variants, one with a Xilinx FPGA and one with a Lattice FPGA, I believe. And the idea there is you can implement open source, fully open source software controllers, as well as all of the low-level hardware features for various monitoring functions. And it can be fully visible and open source to everybody. So LibreBMC is that hardware effort. So with Lattice's support, we're moving forward with a Lattice implementation on the module here. So you can see the ICE40s, which are Lattice devices, are doing this aggregation to bring all of these sideband IO in, and we've got. You notice we're using the LVDS tunneling potentially across some of these other interconnects for the topology interconnect if you want to carry them as a sideband. So that's basically the layout of the module at a very high level, and but that's the core of the logic. Obviously, the other piece of the module is the power. So that's the module we're starting with. But like I say, we don't want to get too far ahead of our skis in that module design until we know we've got a good thermal and power infrastructure here. And that's been something that's actually been evolving quite rapidly. And again, OCP and these efforts have been driving quite nicely. These module efforts have been driving the power industry quite nicely. So we've made quite a good bit of progress in the last year compared to when the last time we analyzed the power situation. You know, when you want to deliver 1,000 watts plus. So the objective of where I'd like us to go next is we want to prototype one of these HPCMs. but we've got this radical power and thermal infrastructure architecture. So we want to really build some prototypes and test out this as well as simulate it. So to do that, we'd need to build an HPCM load power test module. And we'd also need to build an E3.S load power test module so we can show that we can actually successfully cool these media modules as well. And in that, I should have deleted that. In that, we want to emulate the distributed power across the module because we've got some conductive cooling going on there that we need to analyze. Once we've got those two modules, alongside that, we're going to need to design and build the HPCM, the main processor water cooling prototypes. And I think we've got a couple of options for cooling the main HPCM, the kilowatt processor. And we have to design and build an E3.S conductive water cooling prototype as well. So, and then we need to test it all. So just looking at the first one, building an HPCM load power test module, this is the progress that we've actually seen. So that at the very top on the right, so well, first of all, before I get into the detail of the pieces, on the top right, Roger Beeston is on the call, the CEO of Prog Analog, and they've got these active load slammer adapters, and they've got one in development for the AMD Versal VP2802, which is in the 1802, which is a device of the module we're actually building, which is great news. So we can actually, that is an adapter with the footprint of that particular device, which is, this shows the package is VSVA 5601. It's a 70mm by 70mm package. And so that is going to be our base design for the module I just went over. So the effort going into the power infrastructure of testing this will also then feed into creating the real module itself. But we can do this in some piecemeal steps. We want to architect the power supplies to be a 1.4 kilowatt power delivery. And so with the progress that's been made, looks like OCP or the various hyperscalers and big processor companies have pushed the power industry into some industry standard modules. So you can see there that there is an MPS 130 amp two-phase power module, a tiny little power module there. And also there is, this is MPS's version. Again, these are standard footprints, so I assume they're available from other people or will become available. There's a 1 kilowatt, a 54 volt to 12 volt power module there. And MPS have interestingly built their own little power module in the OEM format to show what you can do with these power supplies in the OEM format. Now their makeup is all that they've got those huge screws, those huge bolts for you to put your loads in. We want to be a bit more advanced about that. We want to put a real device in. So that's where Prog Analog's load slammer chip is going to come into play. So sorry, let me just.
Alan, to be clear, this prototype you're building, is this going to go into a thermosiphon type setup as we discussed on the last call?
Well, good question. let me just switch back over to the model if I can. Is the model going to be? I just want, for people that are new to the call, I wanted them to see this. This is going to take a bit of time to load, but essentially it's the same. So we need to build a prototype of the wall. We've got this wall infrastructure which provides the cooling. We were cooling in a vertical column of 16 HPCMs, and I showed a pumped infrastructure with control. And what Greg is talking about is the potential to turn that into a thermosiphon approach instead. So at this point, Greg, I'd say no. We're just looking at an individual module. I'm thinking of maybe we implement a radiator type to cool a single module where we can pump the water around. Maybe we actually leverage some of the very low cost water cooling solutions from all these third-party companies for gaming PCs.
Yep.
This prototyping level, it's all about making the blind mate connectors and making all of this work, but doing it from just from a get this up and running. Can we cool this? And if we can control the flow of the water, we can also do a little control loop on a single module that we can.
Yeah, I mean, the reason I ask is because your thermodynamics are going to be different with a phase change that you're going to experience in a thermosiphon to just using a liquid phase only.
Yeah, well, at the moment I'm still in the liquid phase only because that's what we've architected here. But again, this is where the exploratory investigations could get. That's why I said we really want to nail this down. In the moment, we'll stay in liquid.
Yeah, my team might be up for investigating that.
Well, so that's part of this plan is how do we go about this? So I don't want to say this is the way, but so if the experts say we can make this into a thermosiphon 2-phase, then the question becomes how and what do we need to change in this thermal architecture to make that happen. But at the moment, I'm running with this assumption. So just for everybody here, this is a wall. All the new people, this is the wall of this is 16 modules high per column, and this is just showing a small section of a wall in the data center of eight modules. I built one for Frontier as well, where it was 50,000 modules. At the bottom, you can see one of our modules is plugged in, but this is the wall infrastructure here, and we had a single cooling loop for the 16 modules per column with a pump and a heat exchanger to go into the infrastructure cooling facility water. So that was what Greg was referring to there. So at the moment, so this is the how can we build the cooling here, and so I've said potentially we can do this is conformally coated. We would actually, you'd actually do this University of Illinois innovation of conformally coating copper over an insulation layer and then running the water across that. So that could be one experiment. I think I meant to put it on a different slide, so apologies. Let me just go back to this. With regards to the E3.S test module, I've just shown in the picture an example of a CXL version of these, but it's pretty typical. You have a controller chip that may burn most of the 25 or 40 watts of power. And so I said, for example, about 15 watts. So we would put a power FET down there in a similar way to Roger's load slammers implementation of a module. We'd do something similar for this, but we'd also distribute lighter load FETs to represent the way the power is spread across the module. So we could simulate a module thermally here as well, potentially. And that would then thermal conduct down, as I've shown in our previous models. Sorry. So on the actual liquid cooling, we showed the module was we had 16 sites, right, on the full design, and I thought that was going to be a little bit complicated for us for Ender to do the thermal model. So Ender, I'll send you this model over our shared team group later today.
Okay, thank you.
But basically, I've simplified it down to if we could build a test vehicle of one single slot, this is where we can experiment with our ability to cool these this new sort of idea that I had of being able to conductively cool with these spring-loaded like electrical type connectors, but for thermal transfer. I think that's going to be a critical area. I think it might be difficult to accurately model that. So building this would be great. I don't think we have anyone on the call from Samtec today. Shout if you are there. But I was hoping that maybe Samtec could help us make these little spring-loaded connector things for the thermal conduction. So we could build this. So this would be, and you'd have just a basic inlet and outlet there to use. And as well, in this little test module, I thought we could also take the opportunity. We were talking about conductively cooling the active cables if you had silicon photonics in there, or just a retimer, redriver built into these small connectors to replace these huge QSFP cages. And so a water cooling attachment there on the active cables might be a nice feature. So that's that. I just did a little bit more of a slide on this conformally coated. So I just showed that picture we've gone through before from the University of Illinois research, which is conformally coating a board, initially insulating it like the military did for hermetically sealing these boards, and then conformally coating this copper layer. They've got ongoing research there. I said potentially our platform could be a good research platform for them. And then we would need to build a water chamber lid to go over this copper that would pour the water in and be watertight, and have inlets and outlets of the water. So I haven't done a 3D model of the test prototype there, but I was thinking that we could sort of feed that in as another sort of separate little test. And I'm sort of torn between whether we do, at what point do we put the entire module together with all of the pieces and the water flowing through everything, to the water flowing through these separate pieces. And to a certain extent, I think doing the separate pieces could help with Ender's thermal models, and I need to talk to Ender and Chate a bit more about that. But that could be a possible way forward. Yeah, go on.
Alan, I had a quick chat with our SMC line guys the other day, and they were saying that conformal coating is something they do on quite a regular basis because a lot of their work is military. The innovation here, as I understand it, is by using copper, it's a lot more thermally conductive. It's not necessarily conformal coat. There is quite a lot of conformal coating that goes on out there.
Yeah, conformal coating is very old.
The innovation is the higher heat transfer capability of using a metallized layer.
Correct.
Is that it? Yeah.
But there is an initial insulation layer, so you don't short everything out. And then you do. So the idea is a very thin insulation layer and then the copper layer on top. And it's a lot. They claim it's 700% more efficient heat transfer than a paste with a copper tank on top. And obviously you don't have all of the cityscape issues of the undulating heights that are a big challenge. It is still research, and so going down that avenue is certainly one that I think our module is really nicely suited to what they're doing, because I think we can hermetically seal a water lid on top of this quite easily. So if we could get funding from somebody, it would be great to experiment with this. But I think in parallel, we also want to 3D print a water chamber, or manufacture somehow. My head is going towards 3D printing for various reasons. A standard water chamber that we could attach to the device as well.
Alan, one question I would have on the conformal coating, in addition to just, I think I mentioned previously, just being curious about like lower surface area for heat transfer, but I guess that would all come down to testing and simulation. But I am curious about serviceability. I know oftentimes it's a requirement to service the different components on the board, whereas I imagine this is not serviceable at that level.
Yes, so that's the serviceability of conformally coated boards. I think we would need to go back to the military world, but I remember from my old days, and I'm talking decades ago now, that it may well have been a challenge. And with this extra copper layer, I'm sure it would be even more of a challenge.
I mean, do HPC shops though really service boards, the
Well,
super
so
thing.
right, Greg. That, I mean, so in my mind, you've got a couple of problems that go on, Callum, when you've got a module. When you've manufactured the module, you want to make sure it works, right? So you want to make sure it's functional and everything's connected and there are no completely duff devices, right? So you could do that before you go for the conformal coating. It could be part of the manufacturing test. But then you want to test it. You also want to test it at full load, which arguably you couldn't do if you didn't have the conformal coating, unless you had some sort of more old-fashioned way of initially testing these. But maybe you couldn't test them to the full power requirement of what you could call with this, let's say. So there's that system level test, and then there's this bathtub curve of, you got the early failures, right? And if you get a failure, can you recover it by rework? And that's where you wouldn't be able to, that bathtub curve roll off of recovering a faulty board. So that's a fair point.
Yeah.
I think the argument goes, though, if you look at chiplets, if you look at what AMD are doing with their MI300 or NVIDIA with their devices, there's so many, they're talking about getting up to 3 kilowatts now. There's so many, you're never going to rework those over. And to be honest with you, all of the value is in those chips. And I guess, obviously, if you lose a power supply, you'd want to rework that. But if you lose that chip, then pretty much that's the whole value of the module in reality.
I think this is where graphene coating makes a lot of sense, because you've got to coat with something like PTFE or PET anyway. It bonds much better than the copper will, and I've still got massive issues about copper's corrosion. That, I think, is the main serviceability issue with this approach, is copper does corrode over time with contaminated water.
Yeah, I'll tell you what, we're getting into the weeds, and I don't want to give.
Yeah, you're right. I'll shut up now.
Really, this is trying to outline the plan of what we're doing. Not get into the detail, but this is what we want people to be working on. Yeah. But to that point, anyway, I really think we should do a 3D printed copper coolant version as well, because this is still research, and all the points that have just been brought up are all valid. But I think this is what we're here to do, because we're trying to radically re-architect the way we build the data center. So these are things that we need to resolve. So basically, we could combine everything together. And maybe that's when we build the full cooling approach, where the water is flowing through everything. And we need to be able to deliver the full 1.5 kilowatts. We need to get a power brick. We need to build an equivalent of the wall. Maybe it's 1 HPCM or 4 HPCMs, which is the equivalent of the wall, a desktop version. And maybe we can integrate a little local heat exchanger, air coolant to air heat exchanger radiator, like one of these gaming radiators. So that was that. I want to quickly hand over to Ender. He's got basically he's trying to build a model. He's looking at what does he need, and what can we delete from the model to make his simulations easier. As you can see, I've done a little bit of work here, maybe for the E3.S. But Greg, but Ender, would you like to, if I stop sharing, would you like to share?
Okay, Alan, let me share my screen. As Alan pointed out, we are focusing on the development of thermal models of the HPCM, a liquid-cooled thermal model, by means of numerical simulations. We have to discuss which components should be considered or included in the thermal model, because a multi-region computational model will be used, where governing equations will be solved at each region, such as air, water, and solid. So in order to reduce the computational mesh and time, we have to discuss which components will be included or excluded, depending on the thermal perspective. We opened the three-dimensional geometry by CAT viewers. So the first component is the cable assemblies here. There are 8 cable assemblies on this model. So the question is, these components will be considered or not?
Well, I think not. We can take those out, except for maybe we have one of them to do it. It would be nice to do an active simulation. I don't think there's going to be a problem cooling those compared to cooling the E3 modules. So I take them out for this first order. I wouldn't worry about it, Ender.
Then the second component is MCIO connectors here, that the MCIO components will be connected to these connectors. So we are planning to exclude these components in the thermal model, if it's okay.
That makes sense.
Okay. The other component is the mounting screw. There are some radial parts on this component. So if you want to include this component in the thermal model, we have to create a computational mesh around these components. So this will significantly increase the computational mesh, so computational time. So these components can be excluded in my thermal perspective.
Yeah.
Okay. The water connectors exist on the thermal models. So we will create thermal patches on the surfaces. So our plan is to remove these components from the three-dimensional geometry of the HPCM. So here inlet and outlets of the water to the HPCM can be created as surfaces. So our plan is to remove these water connectors and create surfaces or patches at the bottom of the HPCM, where water enters the domain and leaves the domain from the inlet and outlet respectively.
So I guess on there, as long as you're representing the diameter of the connector as it goes in, you know, what in terms of the flow, then that'll be fine, I guess. You don't need the complexity of that for sure.
Okay, as I said, our aim is to simplify the geometry at the first step. Maybe we can include these components at the next versions of the thermal models in order to see some final results.
Yeah.
The components at the bottom of the HPCM can be classified as connectors. The 1 kilowatt CPU beneath the motherboard. And there's a plate between the CPU and the motherboard in here. Maybe I can zoom to see better. Then bottom chamber and backing plates will exist in the thermal model. So the questions are related with the material properties of these components in order to accurately simulate the heat conduction over these components. I think we need to specify the material properties on this document.
Yeah, and so the one thing I'd say on here is obviously this is going to be the full model. So when we get to the full model, I think like this back assembly, the backing plate, that new model of a single slot that I've created with water in and water out of a single slot, I think that would be a good first step for us to model, and then we can roll it into a complete unit like this of 16. Now my head was in the area that this plate here potentially would be copper, obviously all hollowed out for the water flow to the appropriate water flowing. So my head was out that the backing plate there was copper. In terms of, obviously the motherboard is your standard PCB materials. I'm sure it'll be a high-speed one rather than your FR4. So I don't know. There's tons of high-speed ones now. I lose track of them. Megtron 6 or Megtron 7 is probably one to assume there. But again, the motherboards are quite complex because they have lots of copper in them as well. So we normally do a simplified model that I've done in the past of the conduction properties of the motherboard. If anybody has any ideas on that, then that'll be good input. I guess we've lost. I think we've lost Callum.
Any idea about the material properties here, or?
Yeah, that's what I'm saying. It'll be based on the base material, which is like Megtron 7, let's say, and the copper. How much copper is in the various layers? So it'll be some sort of hybrid. I could ask. I've got one of my old colleagues I could ping and ask him what he does for the PCBs normally. I can get you maybe a conductivity.
Okay, we can add this information to the document later, maybe. There are thermal connectors at the lateral and bottom sides of the HPCM in order to increase the heat transfer between components in order to benefit from the thermal conductivity. So we can specify this material as copper in here. And
I'm not sure that we can. I think that's where we need, it's a shame Samtec aren't on to take the action, but I think that's where, I'm not sure how the connector, the connectors are gold plated something, and I believe they're not copper because the copper won't have the springiness that you need to return back, if I understand correctly. So we need to find out what is that metal that they use. We need to make a decision on if and how we coat that, and what, plate it. And also I'm thinking if we could put some sort of gap pad material behind it as it gets mounted there, as you squeeze, as a module gets plugged in and squeezes those springs, you get the gap pad sort of gives you a better thermal conduction to the overall cold plate. So this is where I think it's going to be a bit tough for us to model this. This is my biggest concern of accurately modeling it first time. And why I want to build an individual one to actually calibrate that as well. But yeah, there's complexities. I think there's a bit of gap pad and what is that material. So we should take an action to ping Samtec and see if they could tell us what material they use for the connectors, and we'd use something similar, is my impression.
Alan, given the complexities of these sprung-loaded mating points, etc., which will inevitably cause some thermal resistance, is there a reason for taking the singular universal approach of pumping liquid around the modules?
So that means we would have to have a separate blind mate water entrance for every module, and that these modules are 25 to 40 watts. It just feels a little bit overkill, and the complexity and cost.
Well, this doesn't seem that simple either. As a reason, I was just trying to test the assumption.
These types of connectors are stamped out by the billion by the connector companies.
Yeah, by OAP folks. Yeah.
But yeah, you need to attach it. So you're right. In fact, the manufacturability of this piece in volume is my single biggest concern of the cost. But the only thing is, this would be identical for every single module. So if you were building a Frontier machine, you'd be building 50,000 of these. So the manufacturability and the ultimate cost of this is huge. So as we design this, we should have a good understanding that we can get the cost down to, ideally below $100 for one of these.
I think it might be worth trying to run the two ideas in parallel until you really know, because you are going to get obviously much better thermal performance with it, and there's just the simplicity of design. If you have one common approach to the thermal management for every layer of the system, then you get good at it. You reuse the knowledge learned in every part in every other part. Yeah, it's just a thought. I totally appreciate what you're saying about the complexity of the blind mate connectors, but yeah, there's.
Well, it's the cost as well. I understand those Stobly blind mate connectors are not cheap. I don't know if so that's something we need to be aware of.
Okay.
Because we'll have basically 32 of them on top of the 4 we've already got. So, and there are additional opportunities for leaks and all that as well, obviously.
Yep. Okay.
But yeah, point taken. I guess it's a balance of what we're trying to cool here, and the simplicity of the approach.
Yeah, there is a beauty in the simplicity of just a thermally conductive material. Sorry, I'll shut up now.
I did have a wedge lock approach before, but it was then these walls were really tall. Okay, Ender, we're a short time, so yeah, so it's not copper is the answer to that, but we need to find out.
And the last one is the E3.S OMI memories. So there are 16s on this module. Heat production is available, so we need to specify the material and the total power generated by this module.
Right, so I think we want the 25 watt, which is a single width version, in the 40 watt. I'd like to be able to call the 40 watt in a single width format. Is a sort of goal that we get that extra power density. And as I explained in my slides, it will be good for us to get the power sources distributed across the module, and with the controller and at the bottom nearest where the cooling is going to be most of the wattage of the module, like of the order of 15 watts, and then the other 10 watts and a 25 watt one would be in the media. Is sort of my rough, and you'd spread that out. So your thermal model would need to be representative of where the power sources were, and then you'd have a unibody case that would probably be aluminum, where so again you and I can maybe work on building a little thermal model for the module, and then the lid. I've sort of shown the lid is copper there. I don't know if it needs to be copper, but that's what I've got there at the moment. It could be aluminum, maybe. It depends how the thermal simulations go, I guess. That guide us.
Okay. That's all from my document in here, so
okay,
I'm stopping the screen.
All right, well, it's good to be getting started on that. And that was very good timing. We're at the top of the hour. So I did want to say about conferences. So I've put something in for OCP, for the OCP Global Summit, to give everybody an update. I think Ender is putting something in for the Future Technologies Symposium based on what we're doing here. I was going to put some more in as well, another one maybe for Future Technologies. I'm going to the Composable Memory System meeting on tomorrow, and I'm going to be presenting on what we're doing for here from a perspective of the CXL enablement. So those guys are working on the management side, the fabric management of CXL, and so I'm presenting this, and I present the Lattice. The main guy from Lattice is coming along as well, so he'll be able to talk to the BMC side of things there. And supercomputing, I'm thinking of applying for a BOF, and so when you have a BOF, it would be good to have a panel of people bringing something to the table of what they believe, why they believe in this, and what they're maybe doing to help us make this become a reality. The last BOF I did, I had Lawrence Livermore Labs, I had Trent DeHuge, and I had Bill the OT CTO of NASA, and I think Roger Beeston was, I'm not sure if he's still on the call. Roger was on the panel, and I think I had one other person as well. Oh yeah, we had Boyd on as well, Chris from Boyd. So I'm planning on doing another BOF. I think if we can get that, we've got a July deadline to get that in. So if people are interested on the panel, let me know. On that note, I'll let you all go, but thank you very much for your time.
Thank you.
Thank you.
Thank you, Alan. Yeah, have a nice day.